We finish off section 2.5 with determinants and the inverse. So there's a very close connection between determinants and inverses of square matrices. In actual fact, the determinant completely determines whether or not a matrix is invertible, as the following theorem is going to state. So it's theorem 2.5.23 in the textbook, and it says an n by n matrix is invertible if and only if the determinant is not equal to 0. So we are going to prove one way, and the other way is going to be left as an exercise. So assume that the determinant is not equal to 0. Now, by theorem 2.3.7, that means there exists an n by n matrix B in row echelon form, so that A and B are row equivalent. So basically what it means is we are saying we've got a matrix. If we do elementary row operations on A, we will get to row echelon form at some point, and that's what we are calling B. So by theorem 2.5.14, there exists a constant K, so that determinant of B is equal to K times determinant of A. So remember, in the set of row operations, we have got row interchange and scaling of rows. That is what affects the determinant of a matrix. So in other words, those two, if we think of those two set of row operations, that they possibly are there when we do row echelon, when we reduce A to row echelon form. So that means that determinant of B will be equal to K times determinant of A for some K that is not equal to 0, right? Now, so what it means is the determinant of B is equal to B1 times B22 up to Bnn, because B is in row echelon form, and that is not equal to 0 because we know that the determinant of A is not equal to 0 from the hypothesis, and also that K is not equal to 0, right? So so in other words, every entry in the diagonal, in the main diagonal of B, is not equal to 0. Now this means that if we look at theorem 2.3.15, this means that the system has exactly one solution, and the solution is obviously the trivial solution, the solution where x is the 0 vector. Now we know that A is row equivalent to B. So what it means is theorem from theorem 2.3.6 that the only solution for the system AX is equal to the 0 vector is also x is equal to 0 is equal to the 0 vector, and this is because the system A's 0 is row equivalent to the system B is equal to B, the 0 vector, right? So therefore, if we use theorem 2.4.7, we know that the matrix A has to be invertible. If the only solution for AX is equal to the 0 vector is x is equal to the 0 vector, we know that means that A has to be invertible. And then as we mentioned in the first instance, that the converse is left as an exercise, and that's exercise 2.5.3 number 4, right? We have got another result on inverses and determinants, and that's theorem 2.5.24, and it says if A is an invertible matrix, then the determinant of the inverse of A is equal to the 1 over the determinant of A. And The proof is also left as an exercise. That's exercise 2.5.3 and number 5. So if we collect the results that we have now, we have theorem 2.5.25, and it says let A be an n by n matrix, then the following statements are equivalent. Number 1, A is invertible. Number 2, the only solution of the equation Ax is equal to the 0 vector in R is x is equal to the 0 vector. And number 3, the equation Ax is equal to B has a unique solution in Rn for every B in Rn. And then the addition to that is the determinant of A is not equal to 0. So this is just a collection of results that we already have, and the proof is left as an exercise in exercise 2.5.3 number 6. Right, so let's look at an example. So suppose you are given a system of linear equations, kx plus y is equal plus 2z is equal to minus 3, 3x plus 6y plus kz is equal to 2, and minus x minus 2y plus kz is equal to 1, where k is a constant. Then we are supposed to determine the values of k for which the system has a unique solution. Right, so we write our system in matrix form, where A is the coefficient matrix and B is the column vector with entries of the right hand side of our system. Now we know that so we can calculate the determinant of A, and that is equal to 8k squared minus 4k. So for the system to have a unique solution, we know from theorem 2.5.25 that the determinant is not supposed to be equal to 0. So in other words, we can find all values for which k is equal to 0, and then we don't want those values. So if we do that, we see that k is equal to, so for 8k squared minus 4k to be 0, k has to be equal to 0, or k has to be equal to plus or minus 1 over the square root of 2. So we don't want those values for us to get a unique solution. So in other words, the system has a unique solution if and only if k is not equal to 0, and k is not equal to 1 over root 2, and k is not equal to minus 1 over root 2. Right, so we have another result which is called Cramer's rule, and this helps us in finding explicit values for or finding an explicit solution if the solution is a unique solution. So it is possible to express the solutions of this system directly in terms of the determinant of A, and this is what is known as the Cramer's rule. Right, so that's theorem 2.5.27. So let A be an n by n matrix such that the determinant is not equal to 0. So for any B in Rn, the unique solution of the system of equations Ax is equal to B is equal to x1 is equal to determinant of A1 over determinant of A, x2 is equal to determinant of A2 over determinant of A, up to xn is equal to determinant of an over the determinant of A for all the j's from 1 up to n, and the matrix Aj so is obtained by replacing the entries of the jth column of A by the entries in the matrix B, so the column vector from the system of equations. And so we're going to illustrate this with an example, and that's example 2.5.28 in the textbook. So we want to solve the system of equations, and the system of equations is as given. below, and then so we write the system in matrix form: AX is equal to B, where A is the coefficient matrix and B is the column vector whose entries are the right hand terms, right? So for us to find, so we can find the determinant of A, we can expand using the first row because it has a 0 there, and we find out that the determinant is 44. Now we want to find determinant of A1, determinant of A2, and determinant of A3. So we have to find the matrix A1, A2, and A3. So A1, we replace the first column with B, so we get that. And for A2, we replace the second column with B, so we have that. And then A3, we replace the third column with so the third column with B, and we get that. So if we find the determinant of A1, we see that it's minus 40. You can do the you can expand using the first row, and for A2 you can choose whichever you want because there are no zeros anyway. We get 72, and for A3 you can expand using the first column or the first row or the second column, and you see that it's the determinant is equal to 152. So therefore, by the rule, by theorem 2.5.27, our solution becomes x1 is equal to 40 minus 40 over 44, x2 is equal to 72 over 44, and x3 is equal to 152 over 44. And that is all for this video. Thank you.